the name of Almighty God, I'm Master Sankosha, and today I want to talk about Introduction to Battery Design Module in Computer Multiphysics Simulation Software. Now I want to go through the model wizard. To start the software, double click the Computer Multiphysics icon on the desktop. When the software opens, you can choose to use the model wizard to create a new computer multiphysics model or blank model to create one manually. For this tutorial, click the model wizard button. If computer multiphysics is already open, you can start the model wizard by selecting new from the file menu and click models wizard. From the file menu, choose New. In the New window, click Model Wizard. In the Model Wizard window, click 3 dimension. In the Select Physics tree, select Electrochemistry, then select Batteries, then select Lithium-ion battery and click Add. You see, we have electrochemistry, and for electrochemistry, we have a primary and secondary current distribution. Then we have primary current distribution, secondary current distribution, tertiary current distribution, next blank tertiary electron neutrality, tertiary water based with electron neutrality, tertiary supporting electrolyte, and tertiary Poisson. Then we have a batteries, lithium-ion battery could have form geometry. Lithium-ion battery, single-ion, and battery with binary electrolyte, lead-acid battery, lumped battery, two-electrode battery, equivalent battery. Coded secondary current distribution, coded tertiary current distribution, next blank, coded current distribution boundary elements, coded current distribution on edge boundary elements, and you can finally click on study. In the Select Study tree, select Preset Studies for selected physics interfaces, then select Time Dependent with Initialization. Click down. Now I want to go through the geometry one. The model geometry is available as a parameterized geometry sequence in a separate MPH file. Load it from File with the following steps. In the geometry toolbar, click Insert Sequence and choose Insert Sequence. The next step is browse to Models Application Library folder and double-click the file Patch Cell Utilization Geometry Sequence.mph. Note that the location of the files used in this exercise may vary depending on the installation. For example, if the installation is on your hard drive, the file path might be similar to C slash program files slash console slash console 64 multi-physics applications, battery design module, lithium-ion batteries, performance. In the geometry toolbar, click Build All. In the Model Builder window, under Component 1, click Geometry 1. Since the geometry has now been finalized, you may now collapse the Geometry 1 node in the Model Builder window. Change the scaling of the graphics window. The cell geometry has a higher aspect ratio, with the cell thickness being very small in relation to the cross-sectional area to facilitate setup. The physics charge the scaling in the z direction as follows. The camera in the model builder window, expand the component 1, then select definitions node, expand the view 1 node, and click camera. In the setting window for camera, locate the camera section. From the View Scale list, choose Manual. In the Z-Scale text field, type 100. Click Update. Now I want to go through the global definitions parameters. Some parameters would loaded with geometry sequence into the parameters 1 node. In the model builder window under global definitions, click parameters 1. In the settings window for parameters, type geometry parameters in the label text field to rename it. Add some more parameters from text file. In the Home toolbar, click PI parameters and choose Add parameters. In the setting window for the new parameters, note type physics parameters in the label text field. Look at the parameters section, click Load from File, and browse the Models Application Libraries folder and double-click in the file. Patch Cell Utilization Physics Parameters.txt. You see we have a different parameters. For example, reference exchange current, which is a 0.7 ampere per square meter. Reference exchange current, which is a 0. It's for negative. This is for negative. The first one was for positive. 0.96 ampere per square meter. Positive electrode particle, which is 2 multiplied 10 to the power of a minus 6 meter. Negative electron particle, which is 5 multiplied by 10 to the power of minus 6 meter. Electrode conductivity negative, which is 100 s per meter. Electric conductivity positive, which is 0.8 based on the s per meter. Maximum house capacity is 22,860 molar per cubic meter. Positive electrode volume is zero point 0.5. It's a dimensionless, and maximum house capacity is 31,507 molar per cubic meter. Negative electrode volumetric is 0.45,347. It's a dimensionless. Initial set state of charge, which is dimensionless, is zero point 0.2. Set of charge windows is zero point 0.7, and C rate during simulations for simulation time is 630 seconds. Now I want to go through the add materials. Most of the required material parameters are available in the material libraries. First, add copper and aluminum for the current conductors in the material toolbar. Click the material to open the add material window. Go to the add material window in the tree. Select both built-in aluminum and built-in copper. Click the add to component button in the window toolbar. Next, add the material properties for the electrode and electrode materials. Go to the Add Material window. In the 3D, select both battery electrodes and then graphics, and so on. For lithium-ion battery, you can have the graphite for negative pole, and also lithium manganese for positive ion pole. Click the Add to component button in the window toolbar. Similarly, in the 3D, select battery electrolyte and also liquid lithium ion battery, and click the Add to component button in the window toolbar. In the material toolbar, click Add material to close the Add material window. A red cross may show at the aluminum node at this point, indicating missing the material properties. This is expected and will be fixed later when setting up the physics. Also, no selection warning may be seen at the other material nodes. Now I want to go through the assign the materials to the domains of the geometry. Assign the materials to corresponding material domain. You see that in the model builder window, click aluminium. In the settings window for the materials, click aluminium node. Locate the geometry entity selection section. From the selection list, choose positive current toolbar and tap. The name selections that appear in the list are created under geometry and were automatically included in the geometry sequence file you imported earlier. Proceed similarly for the other material. Click Cooper and the corresponding geometry entity selection section. Choose negative current collector and tab. Click Graphite and choose negative electrode. Click lithium manganese, and for positive lithium ion battery, and choose positive electrode, and also click lithium PF6 for a liquid lithium ion battery, and choose separator. Now I want to go through the lithium ion battery. The geometry has now been defined and we have imported the needed parameters. We are now ready to start defining the actual physics of the problem. The separated node was added to the interface by default. Add and define the negative electrode. Keep the default settings for the separator and proceed to add and set up the physics in the porous electrodes and current collectors. In the physics toolbar, click domains and choose porous electrode. In the settings window for porous electrode, type porous electrode negative in the label text field. Locate the domain selection section. From the selection list, choose negative electrode. Look at the electrode property sections and look at the electrode property section again. For in the sigma s text field, type sigma is negative. Look at the porous matrix property section. In the epsilon s text field, type epsilon negative. In the epsilon 1 text field, type 1 epsilon negative. Particle intercalation 1 in the model builder window, click particle intercalation 1 in the setting window for particle intercalation. Locate the particle transport properties section. In the R peer text field type RP negative. Leave the settings of the species settings section as is for now. The initial species concentration settings will be made inactive later when we define the cell state of charge on a different node. Now I want to go to the porous electrode reaction Y in the model builder window. Click for electrode reaction Y in the settings window for porous electrode reaction. Locate the electrode kinetic section in the I0 reference temperature text field. Type I0 reference negative. Add and define the positive electrode and process similarly to define the positive electrode. In the physics toolbar, click domains and choose porous electrode and rename the node by typing porous electrode positive in the label text field. Locate the domain selection section from the selection list. Choose positive electrode. Locate the electrolyte property section from the electrolytes material list. Choose liquid-ion battery. Locate the electrode property section in the sigma text field. Type sigma positive. Locate the Peirce matrix property section in the epsilon text field. Type epsilon positive. In the epsilon 1 text field, type 1 epsilon positive. Now I want to go to the particle interpolation 1. Click particle interpolation 1 child node in the particle transfer property section in the RP text field. Type RP positive. Now I want to go to the porous electron reaction 1. Kinetic porous electrode reaction 1 in the electrokinetic section, type I0 reference positive. Now I want to go to the current conductor. In the physics toolbar, click domains and choose current conductor in the settings window. For current conductor, locate the domain selection section. From the selection list, choose material metal foil domains. Now I want to go to the electric ground one in the physics toolbar, click boundaries and choose electric ground. In the settings window for electric ground, locate the boundary selection section. From the selection list, choose negative tab end. Enable a state of charge and initial charge distribution. Enable the defined state of charge and initial charge inventory on the lithium-ion battery interface tableau. This will allow us to set the initial state of charge and the battery set. You see, we have a lithium-ion battery and then we have a state of charge and initial charge distribution. Negative electrode domain selection, positive electrode domain selection, separator 1, non-flux 1, insulation 1, initial values from porous electrode for negative pole, porous electrode for positive for current conductor 1, and electric ground. Then sets the initial state of charge of the cell as follows. In the model builder window, click state of charge and initial charge distribution 1 in the setting window for state of charge and initial charge distribution. Locate the initial cell charge distribution section in the set of charge text field. Type a state of charge star. Set the electrode domain selection in the model builder window. Click negative electrode domain selection. In the setting window for negative electrode domain selection, locate the domain selection section. From the selection list, choose negative electrode. Process similarly for the positive selection. Click positive electrode domain selection 1, choose positive electrode. Now I want to go to the electrode current 1. Enabling the state of charge and initial charge distribution node means that the capacity of the cell can be defined at the final current boundary condition current based on the C rate multiple as follows. In the physics toolbar, click boundaries and choose electrode current. In the settings window for electrode current, locate the boundary selection section. From the selection list, choose positive tab and locate the electrode current distribution. From the list, choose C rate multiple. In the C rate text field, type C rate. Now I want to go to the mesh one. Set up the mesh for the model. Use the mesh mapped mesh on the top boundaries and sub mesh for remaining of the geometry. You see more generator, we have a free triangular, free quadratic, mapped edge and vertex. Add a mapped on the topmost boundary. In a mesh toolbar, click the triangle as a more generator and choose mapped. Select boundary 20 only. This is the topmost boundary of geometry. Click build mesh. Add a submesh in the mesh toolbar, click sub. Distribution of mesh element in the negative electrode, right click sub 1 and choose distribution. By the use of distribution nodes, you can control the resolution in the Z direction of the individual layers of the cell. In the settings window for distribution, locate the domain selection section. From the selection list, choose negative electrode. Locate the distribution section. From the distribution type list, choose Beautify. In the number of elements, text field type 50. In the element ratio, text field type 3. Process similarly for the other domains, which different number of elements and ratio settings as follows. Distribution of mesh elements in the separator. In the model builder window, right click, shift bar and choose distribution. In the setting window for distribution, locate the distribution selection section. From the selection list, choose separator. Look at the distribution section. In the number of element text field type 4, keep the other default setting. Distribution of mesh elements in the positive electrode. Right click, shift 1 and choose distribution. In the setting window for distribution, look at the domain selection section. From the selection list, choose positive electrode. Look at the distribution section. From the distribution type list, choose predefine. In the number of elements text field type 50. In the element ratio text field type 3, select the reverse direction checkbox. Now click build mesh. The finalized mesh should now look as follow. So thank you so much for watching my tutorial video until the end. Also, you can download the proper and related and appropriate COMSOL multiphysics simulation file from github.com/masterscript. Today is 24th of May 2026. Time is 8:01 p.m.